Hey everyone, and welcome to our deep dive on something I think is super interesting, hydraulic fracturing.
Yeah, it's amazing what we can do from up here on the surface to access all that energy thousands of feet below us.
Seriously, okay, so first things first, right? What exactly are we talking about when we say hydraulic fracturing?
So at its core, it's a technique we use to get more oil and gas out of those underground reservoirs.
Okay.
It's all about making it easier for those resources to flow to the well bore where we can actually extract them.
And it's been around for a while, right? This isn't brand new technology.
Oh, definitely not. The first commercial treatments go all the way back to 1949.
Wow.
And it's really taken off since then. I mean, just think about this. Hydraulic fracturing plays a part in recovering something like 30% of the recoverable oil
Wow.
and get this 90% of the gas reserves in the United States.
That's a lot. So how does it actually work? What are the steps?
Picture this. We pump a special fluid, usually water-based, mixed with what we call proppant. And that proppant is basically sand or a ceramic material, and we inject this fluid deep underground at really high pressure, enough pressure to actually fracture the rock formation.
So you're purposely making cracks to reach the oil and gas.
Exactly. Those fractures we create are the key to increasing what we call permeability,
Okay.
which is how easily fluids can flow through the rock. So the more permeable the rock, the easier it is for the oil and gas to travel to the well bore where we can get to it.
Oh, okay. So it's like building tiny little highways for the oil and gas to escape.
That's a good way to think about it.
Okay. And you mentioned proppant. What does that do?
So proppant is super important for keeping those fractures open because you see, once we stop pumping that high pressure fluid, the fractures would naturally just close right back up.
Makes sense.
So the proppant, it acts like these tiny wedges holding them open so that permeability stays high and the oil and gas keeps flowing.
So it's like little pillars in a tunnel to prevent a collapse.
Yeah, that's a good way to picture it.
Perfect. Okay, so let's talk about the fluid itself. You mentioned something about viscosity.
Right, so that's basically a measure of how resistant a fluid is to flowing.
Okay.
Like, think about honey, right? Honey has high viscosity, it's thick, it's slow to pour, but water, on the other hand, has a low viscosity, it's thin, and it flows easily.
Yeah, okay, so we want the fluid to be somewhere in the middle to carry the proppant.
We need just the right viscosity for the fluid to effectively carry the proppant deep into those fractures.
I bet that's a tough balance to strike too thick, and it won't flow well too thin, and it won't carry the proppant.
Exactly. It's a crucial part of the design process.
Hmm.
And speaking of crucial considerations, let's talk about in situ stress.
In situ stress, what's that?
That refers to the natural stresses that are already present in the rock formation,
Oh, okay.
the forces that are kind of pushing and pulling on it from every direction.
Okay.
Understanding these stresses is absolutely vital when we're designing these treatments.
So it's like knowing where the rock is already kind of under pressure before you even start.
Yes, exactly, like knowing where it's weak and where it's strong.
Okay.
And we need to know things like the reservoir pressure,
Hmm.
the fracture closure pressure, which is basically the minimum in situ stress,
Okay.
and the maximum horizontal stress. All of these things play a role in how a fracture will form and grow.
So it's not just random cracks, it's all controlled by these forces already existing in the rock.
Precisely, and predicting and controlling where those fractures go and how they'll behave once we start pumping the fluid. That's really the name of the game.
Wow. So there's a ton of planning that goes into this. It's not just pump and pray, huh?
Definitely not.
Okay, so how do you actually predict where the cracks will go?
Well, here's a key point. Fractures, they'll always form perpendicular to the direction of that minimum in situ stress.
So the direction of those cracks isn't random. It's all about the forces already in the rock.
Right, and that's how engineers can figure out how those fractures will form, and then they can maximize oil and gas production while minimizing any potential environmental impact. And when we talk about fracture geometry, we're not just talking about how long the fracture gets.
There's more to it than just length.
Oh, yeah, the fracture width and height are super important too.
Okay.
Like, the height is influenced by things like net pressure and the differences in stress between different rock layers.
I see.
Imagine it like a layer cake, right? Each layer is a little bit different.
Okay, yeah.
And so you don't want the fracture to grow too high because it could penetrate a layer. You don't want to reach like one containing water.
Oh, right. You don't want to contaminate anything.
Exactly. And you also need that fracture to have enough conductivity for long-term productivity.
Conductivity, what does that mean?
That's basically how easily fluids can flow through the fracture. Think of it like a pipe. A wider pipe allows for more flow.
Got it.
And conductivity is heavily influenced by the fracture's width.
Okay, so you need the fracture to go far enough to reach the oil and gas, but you also need to control its height and make sure it's wide enough for good flow.
Yeah, it's kind of a complex puzzle.
Wow. And then you got to worry about fluid loss on top of that.
Oh yeah, that's right. Fluid loss is a big one.
So some of that fluid leaks out into the surrounding rock instead of staying in the fracture.
Exactly. And if too much fluid is lost, it can really make the whole treatment less effective.
Oh, no.
Yeah, because those fractures might not get as long or as wide as we want, and that means less proppant gets placed, and ultimately you get less oil and gas production.
So containing that fluid is really important.
It's a big challenge, and there are actually different types of fluid loss to think about. There's loss related to the viscosity of the fluid itself.
Okay.
There's loss controlled by how permeable the rock is, and even loss that's controlled by the formation of what we call a filter cake on the fracture face.
Filter cake. What is that, like a natural barrier that forms?
Yeah, think of it like nature's way of plugging those leaks.
Clever.
And then you've got something called spurt loss, which is an initial rapid loss of fluid that happens before the filter cake forms.
So like a burst of water when you first turn on the tap.
Yeah, exactly.
Wow. Okay, so how do you keep track of all of this happening thousands of feet underground?
That's where pressure analysis comes in. Monitoring and analyzing the pressure during and after the treatment gives us these incredibly valuable insights into how that fracture is behaving.
It's like having a little window down into the earth.
Precisely, we can learn so much from those pressure readings.
This is incredible. It's so much more complex than I ever imagined.
It is, and we've only just scratched the surface.
Well, I'm hooked. I can't wait to hear more.
Let's dive back in.
All right, I'm ready to hear more about this pressure analysis. You said it's like having a window into what's happening down there.
It really is. It can reveal a lot about how the fracture is developing. It's almost like reading a story written in pressure fluctuations.
Okay, a story. So what are we looking for in that story?
Well, one thing is we can identify different flow regimes, different patterns, and how the fluid's moving.
Okay.
Like early in a treatment, you might see something called pseudo-linear flow,
Hmm.
where the pressure is behaving as if the fracture's extending in a straight line.
Oh, so the pressure data can actually tell you the shape of the fracture.
Yeah, and then as the treatment keeps going, that flow regime might transition to something we call pseudo-radial flow,
Okay.
which indicates the fracture's growing outwards more in a circular pattern, like ripples from a stone in water.
I like that visual. That's cool.
And then there's the pressure decline that happens after we stop pumping. We can analyze that decline using something called a Horner plot.
Horner plot sounds complicated.
It's a bit specialized, but basically it helps us figure out the fracture closure pressure,
Okay.
the pressure at which the fracture starts to close back up.
So that tells you how much pressure you need to keep it open and work at.
Exactly. And even the shape of that Horner plot can tell us more, like if the fracture's still growing even after we stop pumping.
Really? It's still growing even after you stop?
Yeah, we call that length extension.
Wow. So you have to be really careful it doesn't go somewhere you don't want it to go.
For sure. And that's where we start talking about these non-ideal behaviors.
Not ideal. What does that mean?
It means something's happening that we didn't expect.
Okay. Like what?
Well, one example is something we call height recession,
Height recession.
where the fracture height actually shrinks during the closure process. Instead of closing evenly, it starts closing from the top down.
Oh, that doesn't sound good. Why would that happen?
It can happen when the fracture grows into surrounding layers with higher stress.
Hmm.
And then as the pressure goes down, those higher stress layers want to close up first. They kind of pull the fracture height back down.
It's amazing how much you can tell just from these tiny pressure changes.
It's pretty incredible, and we have even more sophisticated tools like GDPDG analysis, which helps us get even more accurate measurements of that closure pressure.
I'm not even going to ask about that one.
It's a bit technical, but the key is it helps us refine our designs and make sure we're creating those fractures with the ideal shape to maximize production.
That makes sense. Okay, so we've talked a lot about the technical side of this, but what about the environmental considerations?
Right. Of course, that's a big part of the conversation, too.
So what are some of the concerns that engineers have to address?
Well, one of the biggest ones is the potential for groundwater contamination.
I bet.
That's a huge priority, and we take a lot of precautions to minimize that risk.
Like what?
Well, first of all, the wellbore itself has multiple layers of steel casing and cement, so that creates a series of barriers to prevent any leaks.
Okay, so it's like a fortress protecting the groundwater.
Exactly, and it's also important to remember the depth we're working at. These treatments are usually thousands of feet below the groundwater aquifers.
Right, so that distance helps too.
Absolutely. It acts as a buffer. And then another key thing is managing that wastewater that comes back up after the treatment. We call it flowback water.
Okay.
That flowback water has to be properly treated and disposed of to prevent any harm to the environment.
Makes sense. So it's not just what happens down there, it's what you do with that water once it comes back up.
Exactly. And there are always new technologies being developed to make the process more sustainable.
Like what kind of technology?
Well, for example, there are recycling and reuse technologies that allow us to treat that flowback water and actually use it again in future fracking operations.
So you're reducing waste and conserving water? That's awesome.
Exactly. And it's a great example of how we're always innovating in this field. Okay, now let's go back to talking about profit.
Right, the stuff that keeps those fractures open, those little pillars we talk about.
Exactly.
I'm curious about the different types. You mentioned sand, but isn't all sand the same?
That's a good question, but sand isn't as simple as it seems. There are actually many different types, and engineers have to think about a lot of things when they're choosing which one to use.
Like what?
Well, one thing is the strength of the proppant. The deeper the well and the higher the pressure, the stronger the proppant has to be to withstand those forces.
Mm.
Think of it like choosing the right kind of brick for a building.
Oh, okay.
The taller the building, the stronger the bricks need to be.
So it's all about matching the strength to the job.
Exactly, and the size of the proppant grains matters too. Larger grains create wider flow channels, which can be good for production,
Right, more
but
less,
they can also be harder to get down into the fracture.
so it's a trade-off.
Right, you want those wide channels, but you've got to make sure the proppant can actually get where it needs to go.
Makes sense.
And then, of course, there are cost considerations too.
Right, different materials, different prices.
Exactly, so you have to balance performance with the budget.
It's like any engineering project, you're always trying to optimize.
Right, and then in addition, sand, we also have ceramic proppants,
Okay,
which are engineered to be even stronger and more durable than natural sand.
so that's for the really tough jobs.
Exactly, and we even have resin-coated proppants, which are designed to improve flow and make sure the proppant doesn't get crushed under all that pressure.
Wow, who knew there were so many types of profit?
There's a whole world of proppant technology out there, and choosing the right one can make a big difference.
This is so cool. I had no idea how much went into this whole process.
It's a fascinating field for sure.
Well, I'm definitely ready for more. What else is there to learn about?
We're just getting started. Let's keep digging.
I'm ready for more. So last time we were talking about the different types of proppant and how they keep those fractures open.
Right, but let's talk more about the fractures themselves, the geometry of them.
Yeah, we talked about length and width and height. I'm curious how you actually control the shape of something so deep underground.
That is a challenge for sure. It's really where the art of hydraulic fracturing comes in.
Okay.
We use a bunch of different techniques to control the fracture geometry, and one of the most important is stress analysis.
Right, we talked about that earlier for predicting how the fractures will form naturally.
Yeah,
But you can use it to control the shape, too.
exactly. Remember, fractures tend to form perpendicular to that minimum in situ stress.
Uh-huh.
So if we understand the stress field in the rock, we can kind of steer the fracture where we want it to go.
Like knowing which way the wind blows and setting your sails accordingly.
Exactly. And on top of stress analysis, we also use these special fluid systems
Okay.
to fine-tune the fracture geometry.
How do you do that?
Well, we can change the viscosity of that fracturing fluid, for example,
Oh, okay.
to control how easily it flows into the fracture and how the fracture grows.
So a thicker fluid makes a wider fracture,
Generally, yeah, but there's a trade-off, right? A thicker fluid is harder to pump.
which costs more money.
Exactly.
So it's all about finding that balance.
Right. And then we have even more advanced techniques like using what we call diverting agents.
What are those?
They can temporarily block off certain sections of the fracture,
Okay.
force the fluid to flow into other areas.
Oh, so it's like putting up roadblocks to redirect the traffic.
Exactly. By controlling where that fluid goes, we can create these complex fracture geometries that are really customized to that specific reservoir.
Wow, that's incredible. It's like you're sculpting the rock from miles away.
It's a pretty amazing process, and we're always working to improve it.
What are some of the challenges you're working on right now?
Well, one of the big ones is improving the efficiency of the whole treatment.
Okay.
Like we've talked about fluid loss, right? Minimizing that loss is a huge focus.
Because every drop that escapes is a drop that's not helping to prop open the fracture.
Exactly. So we're constantly working on new fluid systems and additives that help reduce fluid loss.
More proppant in the fracture, more oil and gas production.
Precisely. It's all about making sure that fluid goes where we want it to go. And then another big challenge is real-time monitoring and control of the fracture as it's growing.
Okay.
So pressure analysis is one tool, but we also use things like microseismic monitoring.
What's that?
That's using these super sensitive sensors that can detect the tiny tremors that happen when the rock fractures.
Oh, wow. So you're listening to the rock cracking.
Pretty much. And we combine that data from pressure analysis and microseismic monitoring and other tools to get this real-time picture of what's happening down there.
It's like having X-ray vision.
It really is. And that real-time monitoring lets us control the fracture in new ways.
Okay.
Like we can change the pumping rate or even what's in the fluid as we go based on what the data tells us.
So you're constantly adjusting things.
Yeah, it's not just set it and forget it. We're monitoring and making changes as needed.
And all of these advancements are making the process more environmentally responsible.
That's the goal, for sure.
This whole deep dive has been amazing. I feel like I have a completely different understanding of this technology.
It's a complex process, but it's so fascinating.
It really is. And it's constantly evolving, too, which is cool.
It really is a testament to human ingenuity, our ability to access those resources.
Absolutely. Well, as we wrap up today, I hope you, our listener, have a much clearer idea of what hydraulic fracturing is and how it works and all the thought and planning that goes into these treatments.
It's a lot more than meets the eye.
For sure. And if we've piqued your curiosity even more, that's awesome. Keep learning and keep asking questions.
That's what it's all about.
Until next time, happy exploring, everyone.
See you next time.